Welcome to the School of Life. Life is hard, but you have got to be harder. I'm Mrs. Collins, your life coach. Let's get started with Unit 3, Lesson 4, Quadratic and Cubic Functions. Our essential questions for this lesson are: how do transformations affect the graph of the quadratic function family? And how do we analyze and graph cubic functions? The very first function that we'll look at is our quadratic function. And we'll look at the parent function for it. So y equals x squared. Some bonus features that you'll find for a quadratic function are a vertex as well as an axis of symmetry. The vertex for our parent function here is 0, 0. And the axis of symmetry will be x equals 0. We'll talk about how this all relates once we graph it. So a vertex is going to be a highest or a lowest point of our parabola. The axis of symmetry, if you could think about symmetry, that's something being cut into half, and on both sides it's exactly mirrored. So again, we'll talk about that as we graph this function. Okay, the vertex, when we are graphing a function and we're creating a table from scratch, we're going to place the vertex in the middle of our table. So here we'll have our vertex and we'll have 0, 0. Around our 0 for our x's, we're going to be very strategic in the numbers that we choose. So I'm going to go backwards in my numbering. So from 0, I'll go backwards to -1 and -2. And I'll also go forwards from 0 to 1 and 2. From there, we're filling out the table of values for our function y equals x squared. So in order for us to do that, we're given our x values, -2 being the first one. We need to plug it into our equation. So we'll have y equals, instead of the x, we'll plug in -2 and then squared. Y equals -2 squared. Well, that would be the same thing as -2 times -2, which is equal to a +4. So this first value is a 4 for our output. Plugging in our second value, you have y equals, we're plugging in -1 squared. That's the same as -1 times -1, which equals a +1. So this gives us 1. Our next value is 1. So y equals, plugging in our 1 squared. This is the same as 1 times 1, which is 1. So we have a 1 here. And then lastly, you have y equals, we want to plug in a 2, so 2 squared, and that's equal to 4. So last, we'll have a 4 here. Okay, with our quadratics in the table, again, if your vertex is in the middle of your table, you should see that each of the values here are mirrored. So like 4 at the top and bottom, as we go 1 down and 1 up, we have 1s. And then our 0 is in the middle. So that's one way that you can see that little axis of symmetry, or that mirrored effect. Let's go ahead and plot these points. So our points have been plotted, and we're going to go ahead and connect our points here so that they form a U shape. So if you remember from lesson 1, quadratic functions form U shapes, which are called parabolas. So we have our U-shaped function. This is what the parent function of y equals x squared looks like. Parent function meaning that this is the very basic function, or this is the very basic graph of our quadratic equations. You'll note that within this unit, we'll see this U shape change. Sometimes it'll get skinnier, sometimes it'll get wider, sometimes it'll move over to the left, sometimes it'll move over to the right, sometimes it'll move downwards, sometimes it'll move upwards. So those are all called transformations. We'll talk about the transformations that we can visualize from the graphs. Okay, your domain, your range, and your end behavior are the next things that we'll identify here. For quadratic equations, our domain is all real numbers, and our range will depend on the lowest or the highest part of our quadratic. And usually you want to look at for your vertex. Vertex being the lowest part of our U shape in this case. So the lowest y value here would be a 0. And then our graph continues upwards. So our range has to do with the possibilities of y's, all of the y possibilities. So this would be y is greater than or equal to 0 for this one. As for our end behavior, we have as x is going towards the left, so as x is going towards negative infinity, our graph is going up, so y is going to positive infinity. As for our right behavior, end behavior, we have as x is going towards the right, so this is going towards positive infinity. So going towards the right, our graph is going up, so y is going towards positive infinity. As we proceed, we're going to interpret some quadratic graphs. And in order for us to do so, we're going to find the indicated information for each graph and think about how each example compares to the parent function. I've kind of drawn in each of the parent functions for numbers 1, 2, and 3. So the parent function, remember, it looks just like the one up above here, whereas our points are listed. Our vertex is at the point 0, 0. Our axis of symmetry splits this U shape into half. It goes through our vertex, which is x equals 0. So all of them here, this is what the parent function looks like for each of these 3 individual graphs. Okay, let's focus in on number 1. For number 1, we're going to list our transformations. So you're looking at from this parent function, how did it shift? How did it move? Did it move to the left, to the right? Did it move up or down? Did it get smaller? In other words, did it get narrower or did it get wider? So we're looking at all of those different things. Has it been flipped upside down, etc., etc. So for number 1, looking at our parent function, I like to always reference the vertex of each of these and knowing where this vertex is in comparison to our brand new vertex. So this vertex was at 0, 0. Our new vertex is here at negative 4, 3. So negative 4, 3. That's our vertex. As far as the transformations, you should be able to see that this vertex was moved to the left by 4. So left 4. And it was moved up 3. So therefore, 2 transformations is left 4 and up 3. Another transformation here, well, it did not get any skinnier or narrower, and it didn't get any wider. So these are our only 2 transformations. The vertex, we can list it as negative 4, 3. The axis of symmetry is the line that splits our parabola into those 2 mirrored parts, 2 equal parts. So in this particular case, our equation here will be x equals negative 4. One common thing that you'll notice is that the axis of symmetry is always x equals the x coordinate of your vertex. Our domain is all real numbers for quadratics. And our range would be our y values, all possible y values. And in this case, the lowest y value is a 3, and then everything above it. So then that would be y is greater than or equal to 3. As for our end behavior, we have x as it approaches towards the right. X as it approaches towards the left, which is x as it goes towards negative infinity. So going left, we're going up. So therefore, y is going towards positive infinity. Your next statement is x as it goes towards the right. So going towards positive infinity. Y is, well, as we're going right, we are going up. So the end behavior will be that it's going towards positive infinity. All right, so we move on to number 2. So noticing our x and y axes, if it was the standard x and y axes, 0, 0 is here. Our parent function would look somewhat like this. So noticing our new graph here, it has been flipped upside down, it's been shifted to the right, and it's also been shifted down. So let's list those transformations. So one thing is there's a reflection here, it's flipped upside down. Another thing is, well, if we follow the vertex, it has been shifted to the right by 4 and down by 3. So right 4 and down 3. Next thing you want to note is, what is this vertex? This is the ordered pair 4, comma, negative 3. So our vertex is 4, negative 3. The axis of symmetry goes directly through the middle, and that equation would be x equals 4. As for the domain, it's all real numbers. And our range, well, in this case we have a highest y value, and then every other y is below it. So therefore, our inequality will be y is less than or equal to negative 3. Negative 3 is the highest y value that we have for this quadratic or this parabola. Our end behavior, we have as x approaches the left, our graph is going down, so down towards negative infinity. So as we're going left on our graph, we're going down. The other statement, as x goes towards the right, so going towards positive infinity, our y's are, as we're traveling right, our end behavior is we will be going downwards. So we'll be going down towards negative infinity. Okay, let's try the last one, number 3. So noting where our parent function is here, we should be able to see that our new graph has been flipped over. So that's a reflection. Okay, in addition to that, if you look at the vertex of the original and the vertex of the new one, it's been shifted one to the right and one up. So right 1 and up 1 are our other transformations. Okay, noting the axis of symmetry for our newest graph, it's here, and that's at the point 1, comma 1. Our axis of symmetry, that goes directly through the middle of our parabola, and that equation would be x equals 1. As for our domain, it's all real numbers. And our range, the highest point, the highest y value of our graph here is a 1. And everything below it will also be included. So we'll have y is less than or equal to 1. Okay. Next we have our end behaviors. So as x is going towards the left, so towards negative infinity, our y is going towards negative infinity. It's going down. So going towards the left, traveling towards the left, our line is going to end up going downwards. As x approaches positive infinity, our y is going towards also, or negative infinity. So as we're traveling towards the right, our end behavior for our graph will be us going downwards towards negative infinity. For number 4, we have our parent function, that's the blue one, and then our new function, which is the red one here. We're comparing what are our transformations. You should be able to see that the red one has been flipped upside down, so once again we have a reflection. Next thing to note is where has it been moved, so have we shifted to left, right, up, down, etc., etc. And in this case, we have a shift of 1, 2, 3, and a shift right, left of 3, and a shift up of 4. So we did left 3 and right 4. You should also note that this newest graph is skinnier than our parent function. So in this case, we actually have that this one is narrower, or we can call it a stretch. Okay, next our vertex. The vertex for our new point is at negative 3, comma 4. So that's our vertex, negative 3, 4. Our axis of symmetry goes directly through the middle. And so it is the equation x equals negative 3. As for our domain, again, it's quadratic, so all real numbers. And then our range, well, looking at the y values here, these y values for this red quadratic or parabola do not go further than R4. So it's all of the y values that are below R4. So that is y is less than or equal to 4. As for end behavior, we have as x is going towards the left, our y's are going down towards negative infinity. As x is going towards the right, our y's are going down towards negative infinity. All right, numbers 5 and 6 are you-try problems. So please pause your video, try numbers 5 and 6, and then resume your video to check your work. And here we have our answers. Please check your work. All right, so here we go on to learning how to graph the parent function y equals x cubed. We're learning more about the parent function for cubics, which is again y equals x cubed. This is the very basic cubic function that we have, y equals x cubed. One bonus feature for cubics is that it has a point of inflection, and for this one, its point of inflection is 0, 0. So very similar to us placing the vertex in the middle of our table when we were working on the quadratics. We'll place the point of inflection, POI, in the middle of our table here. And similarly, we will come up with values for x, so -1, -2, 1, and 2, that were around our 0. From there, we would figure out the outputs. So if we were to plug in -2 into our equation, what would our output be? And so to do that, we have y equals, it was of course x cubed at first. We're plugging in a -2 cubed, and -2 cubed gives us a -8. So this is -8. If we go with y equals x cubed again, we have -1 to plug in, so -1 cubed. And -1 cubed is -1. So this is -1. The next one, y equals x cubed once again. We are plugging in our 1 cubed, and 1 cubed is 1. And then lastly, y equals x cubed. We are plugging in our 2, and 2 cubed gives us 8. So we have our outputs for each of our inputs for our table or for this particular function. The next thing we want to do is graph it so that we can look at see what it looks like. Okay, and here we have a rough sketch of what that graph looks like. Okay, so if you can remember or recall back to lesson 1, we looked at what a cubic function looks like. And remember, it kind of resembles a saddle. So this is our cubic function. All right, to talk about the domain and the range for cubics, both of them are all real numbers for the ones that we'll be working with. So the domain is all real numbers, the range will be all real numbers. For our end behavior, we're looking for the end behavior from the left. So as x approaches negative infinity, our y in this particular example, on the left, or as we go left, we're going to end up going down, so towards negative infinity. As x is going towards the right, as we go towards the right, we're going to end up going up, and we'll be going up towards positive infinity. So that's our end behavior for our cubic. All right, so as we look at our cubic graphs, we're asked to find the indicated information for each of the graphs. Just like we did for the quadratics, we'll compare the graphs to the parent functions. For number 1, we have our parent function listed over here in blue, and then we have our newest graph listed over here in red. One thing that I like to follow around for my cubics is the point of inflection. So I usually compare where the point of inflection is for the parent function to the point of inflection for the newest graph. So for the parent function, it's always at 0, 0. For this one, well, now we have that the point of inflection is at 1, 3. So as we're thinking about the transformations that have occurred, Notice that they're still going in the exact same direction. So from left to right, we're going up. From left to right, we're going up. So it has not reflected at all. But we do have a shift to the right by 1 and a shift up by 3. So it shifted from 0, 0 to the right by 1 and then up by 3. So that's our transformations for this particular problem. The point of inflection is the point 1, 3. Domain, all real numbers. Range, all real numbers for these cubics. For our end behavior, we have as x is going towards the left, our graph is going down towards negative infinity. So as we go traveling left, we're going down. Okay, we'll end up going down. And as we are traveling towards the right, our y values, as we're traveling towards the right, we're going to end up going upwards. So therefore, we're going to end in positive infinity. Okay. Trying number 2. Number 2, it kind of looks like a confusing graph, but I've tried to incorporate our parent function here in blue. Here we have our point of inflection. Again, it's usually at 0, 0. And then we have our new curve. Notice that they're going in 2 different directions. The parent function is going up from left to right, but this one is going down from left to right. So that shows us that we have a reflection. So we have a reflection for this one. And if we follow that point of inflection around, which is at -2, -3 for this one. So -2, -3. You'll see that we had a shift left of 2 and a shift down of 3. Domain is all real numbers. Range is all real numbers. As we're looking at the end behavior, it's as x goes towards negative infinity. Our y, well, let's see. As we're going towards the left, we're going to end up going upwards. So that's towards positive infinity. And towards the right, as we go towards positive infinity, so as we go right, it's going this way, we're going to end up going down. So y is going towards negative infinity. All right, so we have number 3. Again, my attempt at drawing our parent function here on this graph. In comparison to the graph that you've been given, go ahead and try number 3 and then check your work. And here we have our answers. So the next part of our lesson involves graphing functions. For this, we will use Decimals.com in order to quickly come up with our table of values. And then we'll also be graphing and answering similar questions to the ones that we've been answering before. So here's how it goes. First off, we are going to look at our equation that we were given, and we're going to identify those important pieces of information. So remember that in general, we have f of x equals a times x minus h, and then plus our k at the end, remembering what each of those are represented. So in this case, our a would be out in front. It's not there, so it's just a normal 1. So that does not shift or change anything. Notice that we have an h value. That h value is a 1. And we have our k value here, and the k value is our 3. Interpreting what those mean. So that h value of 1 means that we move to the left of 1. I'll write that in black, left 1. And that k value being a 3 means that we went up by 3. So those were our 2 transformations for this equation. Okay. In order for us to graph this equation, what we're going to do is pick out our h and our k. Our h and our k are actually our vertex. So h and k are the vertex. So I'm going to write that there too. This is our vertex. Okay, hk is our vertex, and it goes in the middle of our graph. One important thing to note is that for your h, when you're writing it down, it's going to be the opposite of the number that you see. So it's going to be a -1 here, and then we'll have that 3. So -1, 3 is our vertex. From there, we choose points or values that are around the -1 for the x. So as we're going backwards, you have -2 and -3. And as you're going forwards, you have 0 and 1. From here, I am going to show you how you would figure the rest of this out by using Desmos to come up with your answers or your table of values. All right, so using Desmos, we can use Desmos.com in order to come up with the table for our graph. So when we're graphing, we can use, again, Desmos.com to come up with the tables. So the very first thing that you'll want to do is open up a new tab and type in Desmos.com. Next, we will click on Graphing Calculator. And the equation that we will be graphing here is f of x. F of x is equal to x plus 1. We have an exponent of 2, so we can either use our keypad down here and place an exponent of 2 and then plus 3. Or for that exponent of 2, what we could have done is used our caret key, and it would have taken us up to our exponent range, and we could have typed in our 2. Nevertheless, we have our equation graphed here. So this is a graph of our equation. But when you're looking to figure out the table of values, what you're going to do is press the edit list. And after you've pressed that edit list button, you're going to say convert to table. Here we have now a table of values. If ever you do not see the table of values that you need, you can always take your x value, highlight it, and then type in a different number if you'd like. So like, let's say a -3, and then we can figure out that the output for -3 is 7. Let's say that here we wanted a -4. We can get the output is a 12, and so on and so forth. So do note that you can change the x values to match the table that you have within your own work. And that's how we would use Desmos.com to figure out the table of values that we need for our graph. Or either plugging in each of your x values and then solving, we get the following output. So let's go ahead and graph our new equation. So we had our parent function. Let's graph our new equation with all of the transformations included. All right, so we have our newest equation. Notice that we've taken the parent function and it's been shifted to the left by 1 and then up by 3 as far as where the vertex is. Okay, and then this is that new parabola. When you're doing these problems, it's not necessary for you to actually graph the parent function, but for the purpose of these notes, I want to show you the differences between the parent function and then its newest function that has been created. Okay, for the domain, range, vertex, axis of symmetry, and end behavior, here are the answers. And here are the answers to the domain, range, vertex, axis of symmetry, as well as end behavior. Again, those parts are review, so please go ahead and check your work. All right, for number 2, as far as graphing our equation, first we'll pick out the transformations. And as far as our a value, there's no number there, so default is 1. We have our h, we have a -2 there, and our k, we have a -1. So remember, if we have an h of a -2, then that means that we have moved to the right by 2, and a k value of -1 means that we've moved down by 1. If we are endeavoring to graph our equation in the middle, we're going to place our h and k. Specialty comes with this h instead of this -2. It's going to be the opposite number. So we'll have a +2 there. And then our k value will stay the same, that -1. Find your x's around your +2. So going backwards, you have a +1 and a 0. Going forwards, you have 3 and 4. Use Desmos to come up with the rest of your table. Okay, and here are our table of values. And then go ahead and plot your points. Okay, and we have our new graph. So noting that the vertex, if you want to follow it, it has been shifted over to the right by 2 and down by 1. As for your domain, range, vertex, axis of symmetry, x-intercepts, y-intercepts, and behavior, I'll write those in for you. Okay, two things we haven't necessarily talked about are the x-intercepts and y-intercepts. So in this case, x-intercepts is just where is our red line crossing over the x-axis. So it's crossing here at 1 and also there at 3. So our x-intercepts are 1 and 3. And as for our y-intercepts, where is our line or our parabola crossing over the y-axis? And it's crossing here at 3. So therefore, the y-intercept is 3. All right, for the next problem, let's identify our transformations. You have an a value of 1/2. So that a value of 1/2, that our graph is going to be wider. Okay, and then notice that your h and your k are not there. So we can go ahead and write it at least. H defaults to a 0. And since our k is not there either, k is also a 0. So defaults 0. So when you're thinking about h and k, going in the middle of your table, it's 0, 0. And then come up with the rest of your values, which are here. And then after your list of values, you'd go ahead and plot your points. Okay. That one transformation that we had was that we'd have a wider parabola. Notice that our new one is wider. We haven't shifted anywhere to the left or to the right. The vertex is still here at 0, 0. As for the domain, range, and everything else, here are those answers. Okay, so please check your work. All right, the next thing that we'll do is learn how to graph cubic equations. Graphing cubic equations is very similar to graphing quadratic equations. We're once again going to use Desmos, identifying those transformations, plugging in instead of our vertex in the middle, putting in our points of inflection in the middle, and then walking through the same steps that we've taken several times for the other problems. So first thing, looking at our equation, we have our a value. Our a is a -1. A -1. Let's write that better. A -1. So that means we have a reflection. Okay, if we look at our h, we have a -1 there, and our k is not there, so it defaults to 0. So that h value of a -1 means that we are moving towards the right by 1. In the middle, we're going to place our h and our k. Okay, remember that for the h, it's a little tricky. Instead of that -1, we're going to write a +1, and our k is 0. Coming up with the rest of your values, you have 0, and then -1, 2, and then 3. Use Desmos to find the rest of your values, which are here, and then we'll go ahead and plot them. Okay, so you should note that the black one is our newest function. It is going in a different direction than our parent, so there's the reflection that we have. Note that the point of inflection was at 0, 0 for the parent, but now it's been shifted 1 to the right, just as the transformation that we mentioned by looking at just the equation. All right, and then we have our other answers here. The domain and range are both all real numbers. Our point of inflection was here at the point 1, 0. X-intercept, our black line is crossing through the x-axis at 1. The y-intercept is crossing through the y-axis also at 1. For the end behaviors, they are listed. For the last two problems, you try the last two problems. Find your points of inflections, and then go ahead and use Desmos to come up with your table, graph it, and then find your key information, the domain, range, point of inflection, and end behaviors. And then check your work. All right, and we have our answers for number 2. Number 2, transformations were left 2 and down 1. Notice that our parent function, we have that the new point of inflection is left 2 and down 1 from where it originally is, which would have been 0, 0. Using Desmos, we came up with the following table. Again, noting that in the middle of the table, we have our point of inflection, which is -2, -1. Our domain and range are both all real numbers. And your end behavior, as x is going towards the left, we are going down. So we're going to negative infinity. And as we are going towards the right, we are going to end up going up, up, up towards positive infinity. Number 3 is also here as your answers. For number 3, we had a stretch by 2. And so therefore, you can see that our graph is stretched out vertically. If you want to kind of visualize that, it's stretched out vertically. And so we have its graph here as well. Okay, and all of the information that applies to it, you can go ahead and check your work there. And that's all for this lesson.